Right, first of all, we're going to use the notation which I read as x bar to be the mean of a sample. If I call you collectively 13E, your group name 13E, if I wanted to estimate your mean height, I might just pick 3 of you. I might, for example, pick Chelsea, Corey and Rob. And if I average your heights, that would give me a sample mean. I haven't done everybody, I've just done a sample mean. However, if I had chosen different people, if I had chosen Greg, if I had chosen Siobhan, if I had chosen Sinead and Siobhan, and if I had chosen Billy, I would have got a different sample mean. So maybe I'll call that x1, x bar 1 and that x bar 2. And those sample means may not agree, even though they come from the same population. So overall there's a population of people, the population is everybody, and a sample is some of them. So x bar is going to be the mean of a sample, and I could have different samples. So we'll come back to that bit in a minute. Okay. The population, if we just make a note of what population is, a population is everybody, or if we're talking about leaves on a tree, every single leaf. There's a big tree over there outside the sixth form. If I want to know the average length of the leaves on the tree, I don't think anybody would actually go and measure every single leaf on there. If they did, and they worked out the mean, then they would know the population mean. The population mean, which we denote by mu, that has to involve every piece of data being measured. So we must have every piece of data included. We wouldn't often do that. So that's why we usually use sample means instead. You will come across lots of A-level stats questions where it tells you what the sample mean is, and then asks you to do other things. And you go, well, if you've got the sample mean, if you've got the population mean, what's the point of doing anything else? It's just to make the questions doable at the moment. You'll see that later on. But going back up here, we said that the mean from Chelsea, Corey and Rob, and the mean from Greg, Siobhan, nice to see you this afternoon, Sinead and Billy, those means might be different. So x bar, the sample mean, it won't always have the same value, even if it's based on the same population. So x bar itself is actually a random variable. If it's any consolation, Sinead, I was looking at Kez for a minute, I just thought, I cannot think of his name at all, I've got to choose somebody else. And now it's suddenly come back to me. So, x bar itself is a random variable. It will be different depending on who's in the sample. Okay? What do you think the average x bar should be? If I took lots of different samples here, and then average those averages of the samples, what do you think the average sample average should be? X bar bar? Mu. Yeah, it should get close to mu really, okay? So in the long run, you would expect that X bar gets close to mu. What you expect to happen in the long run, can you think of any notation that might be useful or might sort of sum that up, what you expect to happen in the long run? Yeah. So in other words, the expected value of x bar is mu. That's correct.
So what's the take after in the long run?
You would expect. Okay, you would expect. So we said x bar is a random variable. X bar can have different values depending on who's in the sample. X bar has an expected value of mu. If I did lots of samples, say it's the average height of people in here, say the average height of everybody in here, I don't know, 175 centimetres, 170 centimetres, something like that. There might be some samples where I just happen to pick the 3 shortest people in the group. There might be some samples where I happen to pick the 3 largest people in the group, but most of the time I would just get a representative sample of people in the group. If I drew a sort of frequency diagram showing that, say I know that actually the population mean for you lot of height is 170, and I may have weighed out the shortest person's 160, the biggest person's 180. What do you think my frequency diagram would look like if I worked out lots and lots and lots of samples? Like the normal distribution, it would look something like that, yes. You would get far more sample means here than you do out there. And somebody said it's like the normal distribution. It's actually true that x bar itself follows the normal distribution. We said it's a random variable. It follows the normal distribution. We've already said its expected value, in other words its mean, is mu. We haven't said yet about what else goes in this bracket for the normal distribution. What else goes here for the normal distribution? The variance. Okay. What do you think would make our sample means become closer to the actual true population mean? We can only do things to our sample at the moment. A bigger sample. Yeah, so as the sample gets bigger, you would expect the spread of this to get smaller. The variance of x bar is sigma squared over n, where sigma squared there is the population variance, which you wouldn't normally know in practice, and n is the size of the sample. So as the sample size increases, the spread of these x bars, these sample means, decreases. And if you think about it, that makes sense. This thing here is fundamental to everything else we do in S2. Could you chuck a pen at me, please? Thank you. Thank you. Okay. This thing here is absolutely fundamental to everything we do from now on in S2, and that is called the central limit theorem. Okay, that's called the central limit theorem. It's fundamental to everything else we do. If you look in the textbooks, there's a far greater detailed, thorough, precise where that came from than I've been talking to you for the last 9 minutes and 1 second. Okay? And if you want, it's a good idea to read through that in the book. It gives you exactly sort of where it comes from and it puts more detail on it. But to be honest, if you don't get it or you just think, it doesn't really matter as long as you know that and can use it. Okay? In this example, we are taking a sample of 9 items from a population we are told is normally distributed with a population mean mu of 10 and a population variance sigma squared of 4. We've got to find the probability that the sample mean x bar is greater than 11. So first of all, the question is probability x bar, the sample mean, is greater than 11. That's what we'd write down. And what do we know about x bar? Well, we know that x bar is normally distributed. What did it say in the central limit theorem? In the central limit theorem itself, without putting the numbers in, we had mu and sigma squared over n. Okay? So I'm going to write that down. So in this question then, x bar will be normal. Mu was 10 for the population. The sigma squared was 4. And I have a sample size of 9. So my x bars, my sample means, will be normally distributed. They will have a mean of 10, and they will have a variance of 4/9. And it might be more useful to write that down. Well, what's the square root of 4/9? Yeah, so it might be more useful to write that as 2/3 squared, because it's actually sigma we use in our calculation later on.
Is it the whole thing that's squared? Not just
Here it's the whole thing, the 2/3 is squared. Okay.
Oh, okay.
So, we've used the central limit theorem, and we have this question up here then, the probability that x bar is greater than 11. What do you think you do next? Corey? Yeah, we don't like greater than, just like normal. So we will just turn it into a less than.
Then you just do it normally.
Then you just do it normally, yeah. So it's 1 minus phi of x is 11, mu is 10. The standard deviation you are using for x bar is 2/3. This is a probability concerning x bar, so we're using x bar's mean and x bar's standard deviation here. That value you're phi-ing, I've got down here is 1.5. So can you just check in your table so you can phi 1.5 and then do a taking away and get a final answer? And then we'll explain what we've actually done and what that means. Oh, I thought I'd frozen that and you couldn't see it. So that's what you should have.
Are you supposed to leave it as a percentage?
Oh, you'd leave it as a decimal in the exam. I've said here it's about 7%. Because I want to say, well, what have they actually done? What's this question actually shown us? This question has shown us that if we were sampling from a population, maybe a tree, where every leaf, the average of all the leaves on the tree was 10 centimetres, and the variance of all the leaves on the tree was 4 centimetres, what's the probability if we pulled 9 leaves off at random that the average of those 9 leaves would be more than 11 centimetres? We have worked that out to be about 7%.
So you'd have to do it like 10 times to get that mean.
Well,
You might not have to get this.
yeah.
Yeah, but no expectations 7 times out of 100.
I'll just stop it there for a minute. In this example, we're looking at something which is a different sort of problem, but we can use the same concept. We've got a cubical die, so a normal shaped die, but it's been labelled, so there are 3 1s, 2 3s and 1 6. It's not labelled normally. The die is rolled 40 times and the mean score of each roll is recorded. Find the probability that the mean score is over 3. So what we're doing here is we could work out what the theoretical mean and the theoretical variance are based on our probability skills so far. But each roll here is like a sample. So this is actually like sampling something 40 times. But what we are going to do first of all is define a random variable, because the score on this dice is a random variable. So x will be the score on the die. Yeah, die, not the dice, it's only one of them. What sort of random variable is this, the score on the die?
Discrete.
It's a discrete random variable, yeah, that's right. It's a discrete random variable. What are the values that x can take?
1, 2, 3, 1, 3, and 6.
1, 3 and 6. What are the probabilities to go with those values?
Half.
Because it's 3 out of 6, and that one is 2 out of 6, and that one is 1 out of 6. We said when we did discrete random variables quite a while ago that, yeah, that is its distribution, all its values with the probability that it takes each value. So from there, how can I work out the theoretical, or in other words, the population mean? How can I work out mu? Yeah, you are quoting the formula for the expected value of x is sigma p x for a discrete random variable. That's correct. So if I do 1 times by a half, 3 times by a third, and 6 times by 1/6, and add those up, I will get the expected value of x, which is the theoretical mean. That's a half, that's 1, that's 1. So add those up, we should get 2.5. So the mean score, if we did it, I mean, if in theory, the mean score is 2.5. We don't know what's going to happen on our throws, but it's going to be 2.5 in theory. That's like here the population mean, the theoretical mean, if everything is known and measured. Okay, so what about then the theoretical variance? Theoretical variance, which we will call sigma squared. There's a formula for the variance of x which looks a bit like the one that Rob quoted for the expected value of x. Anybody remember what it is?
Sigma p squared x. Is it x p? X squared p? No, minus x. Minus expectation of
Okay, and this bit here we sometimes call the expectation of x squared. So it's the expectation of x squared, take away the expectation of x squared. With a pause there to show that you're squaring different things. Yeah, okay. So, if I want to work out the expectation of x squared, here that's each x value squared times by its probability. X value squared times by its probability. Are we happy that that's the calculation we would do? Shall I just tell you the answer to that?
Yeah.
9.5. Yeah. Okay. So the variance will be 9.5 on the right. So the variance will be the expectation of x squared take away the expectation of x all squared. So that's our 9.5 take away our 2.5 all squared. Do you want to work that out, or would you like me to tell you the answer? Tell us the answer. 3.25. Okay. So what we have here is x is the score on the dice, on the die, and we have just worked out mu is 2.5, the mean, and we have worked out the variance is 3.25. It's not normally distributed. It's a discrete random variable, but we still know effectively here this theoretical data, or this is data about the population, like if you did it forever, if you knew everything.
Don't you have to square the 3/4?
That is the variance, not the standard. 3/4 is the variance. So that is our sigma squared. Right, now, I said that each roll of the dice was like having a sample. So what we were going to do was we were going to roll the dice 40 times and look at the sample mean. So we are now looking at x bar based upon 40 throws of the dice.
So can you pull the blind down a bit because it's divided.
So we can work out which one it is. Okay. So we're going to roll this dice 40 times, and we are going to look at the mean of those 40 scores. Got that? Rolling it 40 times, looking at the mean of those 40 scores. That is what X bar is. It's the sample mean, the mean of the samples. What can you tell me about how X bar is distributed? According to the central limit theorem, what do we know about the distribution of X bar? What's the first thing I'm going to write down after my squiggle here? N. 2.5, because the mu comes in here. And then after that? Yeah. Okay. No, that's the variance there. So that's fine. So yeah, I've got X bar itself is normally distributed with a mean of 2.5 and a variance of 3.25 over 40. Okay, if you want those as decimals, that's 2.5 and 0.08125. Now the question we had, find the probability that the mean score of our 40 rolls is over 3. So the question is saying, what's the probability that X bar is more than 3? In the 5 minutes or so we've got left, can anybody talk me through what we have to do here? Change it round. Hang on a minute. What about the continuity correction, because X was discrete?
Is it 2?
Oh, we did 3 earlier. Yeah, we did 3 now. Over there, over there.
I like what Billy said best.
Just 3. Just that.
X was a discrete random variable. X bar is not discrete. X bar is the average of discrete things, but X bar itself can be continuous. There is no need to use the continuity correction. Okay? We can just do it without. So, that's absolutely fine as it is. If you just sort of make a note somewhere, there's no need to use the continuity correction. And the reason is that X bar is continuous. Yeah, X may have been discrete, but X bar, the means of various samples, that is continuous. So, we can finish this off before the bell. It's 1 minus phi of, can somebody tell me, what am I going to write in this bracket over here? 3 minus 2.5. Yeah, that's the variance. So yes, down here, that does need to be square rooted. There's always sigma that goes down there. And to speed things up, so I know you're so keen to go, even if it was just 1 second before the bell, because it feels so good to do that. So I'm writing the wrong number in there. 1.754, which is 1 minus 0.9603, which is 0.0397, which is about 4%. So, even though the theoretical mean of this dice was 2.5, if we rolled it 40 times, there's a 4% chance that our sample means will be above 3. And that seems like a good place to stop. So on screen at the moment is just a recap we've put together of what we did last lesson. Most important bit, this bit down here, central limit theorem. X bar itself is a continuous random variable, normally distributed mu sigma squared over n. Doesn't matter what distribution x followed to start with. Last thing I think we did was an example, this one here, cubical dice. We drew up its distribution, probability distribution, and we worked out its mean and its variance, and we then used the central limit theorem to find the distribution of x bar, and we worked out the probability that the sample mean was bigger than 3 was this value over here. And we didn't use the continuity correction because whilst x was discrete, x bar wasn't. That's what we've done so far. We are now moving on to a continuation of this example, which is part 2b, which I think you've probably already got written down on the handout. So part 2b starts off in the same example, find the probability the total is greater than 120. So it's still example 2, but it's part B now, and that is find the probability that the total score, this bracket shouldn't be there, total score is greater than 120. And just to recap what we had previously, we had x was a dice that either gave us 1, 3 or 6, and those probabilities were a half, a third and 1/6. This is what we had last time. And we have worked out already that the expected value of x, which is mu, is 2.5, and the variance of x we worked out to be 3.25. That's what we had last lesson. And we are rolling this dice 40 times, so it's got 40 rolls. I think that's all the information we need to do this next bit. So, did you have this bit of paper somewhere which said example 2b continued? Okay, you've got that. Okay. So it's still the same example, it's continuing, but now we're looking at the total. So, last lesson we said that x bar followed the normal distribution. What I'm telling you now is if you add up lots of x's, they here also will follow the normal distribution. Totals would also follow the normal distribution. So sums of x's follow the normal distribution. I'm just going to write it down again. We had n being 40. So the sum of x will follow the normal distribution. What we've got to work out now is what goes in here. We know that on each throw of the dice we're expecting, on average, to get 2.5. That's our population mean, that's our expected value of x. We are rolling this dice 40 times. What do you think we are expecting our total of 40 rolls
100.
to be? Where did that come from?
2.5 times 40.
Yeah, it is 2.5 times by 40. Okay, that's right. So that is the single x, the expected value of x there, times by n. That is correct. That's just logical, that just makes sense. And if I write the mean down over here I got to write down the variance, and it is just the variance of x times by n that you do. And we've already said the variance of these scores is 3.25, so we do 3.25 times by 40. So the important bit on that line is actually what I've written really small, I suppose, really there. That if you're doing the sums of x's, it is normally distributed with the expected value times by n for the mean, and the variance times by n for the variance, for the sum. So if we've got our distribution, this question was asking us the probability that the sum of the scores, bring that bracket down again, I didn't want to, is greater than 120. And I now have my sum is distributed like this. What would be a good first move if you've got to do a probability that the sum of the x's is greater than 120?
Probability of sum 1 minus 1 minus probability is less than 120.
Yeah, okay. According to the Billy principle, I can put an extra bar there if I want to. Doesn't make any difference. So, can I just go straight into my phi-ing here?
Can you write sigma x?
If you wanted to put in there, you could have put sigma x. Yes, that would be fine. I think that's pretty clear what you're talking about. Yeah. Actually, you can't do what I just said.
Or do less than equal to?
Well, wait, this bit's fine, but the next bit I said, can you just go straight into the phi-ing and do that?
Right.
It's one other thing you've got to do here.
Continuity curve.
Why?
I thought you said you couldn't do it though. You didn't have
That
to
was
do
with the
it.
mean. With x bar can be a decimal, can be an average, because it's an average of the means.
So because discrete, it's not
Yeah,
continuous.
this is just a total of discrete numbers, so it itself will be discrete. So the key thing here is, as the sum, or sigma x if you want to call it like that, is discrete, because you are adding up loads of discrete things, it is discrete, so you do need the continuity correction. So you don't need the continuity correction for x bar, but you do need it for the sum of x values. So what I'm going to do now is just put here a little n. No, I'm not going to do that actually, because I'm not doing that at all. I just need to rewrite this with the continuity correction in here. So that's where we need to be really careful. I was looking before for greater than 120. Now this is where I actually do need to make sure I get this right. Greater than 120 is less than or equal to 120. So what value am I going to use in here?
Does it have to be whole numbers because it's a dice?
The score will be, yes.
So
what I'm saying in here, am I going to put in here 119.5 or 120.5? 120 now. How confident are you of that?
100%.
You're correct.
Even though it's
Okay.
impossible to get half,
Yes.
you roll the dice.
Yes.
Okay.
Because we've had to include 120 here when we turned it round. The only way you can include 120 is if we go up to 120.5. So actually when I said here it doesn't matter whether we put that bar on, and this one it does, really. And that is the correct thing that we have to do here. And now we can just do our sort of normal probability stuff. That's 1 minus phi of x minus mu. Now we said earlier on, if I can just concertina that, mu is this now. This is our mean. We didn't actually work it out up here, although Chelsea did tell us at the time that was 100. Maybe we can arrow that was 100.
Now, is that one on the right, the 3?
This one over here.
Is that squared? Is that already
That is
squared?
sigma squared there, yes. Okay.
So you have to
So I need to work that out and then square root that. Can anybody tell me what 3 1/4 of 40 is? Because I haven't.
Root 130.
Sorry?
Root 130.
Root 130. So that's 130 there. So down here it's root 130. Okay. So I'll pull those lines apart again so we've got everything there. Then it's a case of working out the value of the bracket, doing the phi of it, doing the 1 minus. I'm going to freeze things there for a minute.
I think this one was actually.
Okay, if you're following us on the video, you can see the answers there. I'm just going to stop the video at this point. I think I first had to teach this over 20 years ago here at Kings of Essex. And there's a teacher here at the time who was a legend in their own lifetime, Miss Greenslade, who probably none of you know at all.
I've heard some stuff.
Yeah. She was the second in math, not the head of math, she was the second in math. And she was like my mentor sort of when I started. She was the stats expert in school. She was the person that always taught stats to upper six or whatever. And she said there's one really important example that they have to see and they have to understand. Then they will be able to do upper six stats. It was called the chocolate box example. And I'm going to do it with you now. Okay? It's the same one. It's called the chocolate box.
How was I first?
Do we get chocolate?
Are we worthy of this yet?
You are worthy of it, yes. The time has come where we are going to do the chocolate box example.
I think it deserves its own page.
It doesn't actually. It's not. It's really not too bad. But this brings together the aspects of the central limit theorem and the normal distribution of things, and basically it sort of pretty much deals with every eventuality. So we are dealing with chocolates, which is always quite nice, and we're interested in their weights. And the weight of these chocolates, and I'm going to have W for my random variable here for my weights of my chocolates. W is normally distributed 10, 4, and that's in grams. We're not having chocolates that are weighing 10 kilograms on average each chocolate. So that's in grams. And these chocolates are packaged in boxes of 25. So there are 25 chocolates to a box. We're ignoring any weight of the packaging itself at the moment. And we're going to try and answer 3 questions. Part A, we are going to find the probability that...
What is 25?
25 is how many chocolates there are in each box. Okay. Part A, we're going to find the probability that a randomly chosen chocolate weighs between 9.5 and 10.5 grams. Part B, we're not going to look at an individual chocolate anymore, we are going to look at 25 chocolates, like a box worth of chocolates. Part B, we're going to look at 25 chocolates together, and we're going to find the probability that they weigh between 247 and 253 grams. And part C, we are going to look at the average weight of 25 chocolates. So a box worth of chocolates. And what we're interested in then is the average weight. So we're interested in the probability of that average weight is between 9.9 and 10.1 grams. So I'm going to pause the video there to give you a chance to make sure you've got all that written down. You've had a bit of time to look through this, and someone's just asked a question about the differences between all of these. Yeah. This first one is just picking a single chocolate and looking at its weight. The one down here is picking the 25 chocolates that make a box, finding the average weight of those 25 chocolates and seeing if that average is between these two values. The middle one is summing things together. And those are the 3 possible scenarios that we can get. So part A is nothing to do with the central limit theorem at all. Part A is just a normal probability question. So if we look at our part A, we've got W, it's normally distributed 10, and I'm going to write it as 2 squared this time rather than 4, because that gives you my standard deviation. And I want the probability that W lies between 9.5 and 10.5. And this time it really doesn't matter whether you put extra bars on there, really principle. Going to do a sketch. I want that shaded area. Anybody, any comments?
You can do 10.5 to 10 and then double it.
I could do 10.5 to 10 and double it.
X is less than 9.5 and then do 1 minus that.
X is less than 9.5, 1 minus that. That will give me everything you can see on the right.
And then minus the 9.5 value.
We're getting there. I think you're on the right lines, yeah. What we want, the shaded bit, is everything, take away 2 unshaded bits, and the unshaded bits are equal because of the symmetry here, because this limit is the equal distance below the 10, but this limit is above the 10. By symmetry, the easiest way of doing that is saying it's 1, take away 2 white bits, which isn't what you'd write down in the exam. Okay, basically, if you take 2 white bits away, you get what you want, so 1 minus twice the probability that X is less than
9.5.
9.5, yeah. And then you can just do that as a straightforward normal phi-ing question. So I'm just going to freeze this in the class a minute.
Did you say a negative value is the same as a positive value?
What you should have found is that you're phi-ing a negative.
Yeah.
So you need to do 1 minus phi of the positive.
Oh yeah.
So if you want to look at the board, you'll see that bit is written down if you want to check that bit. If anybody wants to shout out a final answer.
0.1974.
I think it is. Yeah. Okay. I'm just going to pause the video at that point. Stop it for another clip. So part B, the next bit of the question is we're looking at all 25 chocolates together, a box worth of chocolates, although we're not worrying about the box and the packaging. And we want to know the probability that their total weight together of those 25 chocolates is between 247 and 253 grams. So I need now a new random variable for the sum of those chocolates. Let's call it B like for the box worth, okay? This will be normally distributed. Now, what will be the mean weight?
So these are the weight of all the chocolates?
Yeah, the weight of all the chocolates.
250.
Well, yeah, it'll be the mean I have, which is, 10, times by 25. Yeah, so that will be 250. And then what will I do for the variance?
Would you do 2 squared, so 4 times 20?
Yes, that's exactly right. I do the variance of each one, again, times by n. So it might be easier to finally write that down as 250 10 squared. So now what I want is the probability that B lies between 247 and 253. And again, I'll do a diagram. Diagrams can be quite useful. They can help you spot things sometimes more easily as well. So what would be a good way to proceed from here?
Do the same as we did before.
Yeah, because of the symmetry, the shaded thing is everything take away the two unshaded bits, the two white bits. And because each value is the same distance away from the mean, and just take one of them, that's right. So that's the same as 1 take away, twice the probability that B is less than 247.
Does it matter about less than or equal to? Fine.
Here it doesn't, no. Everything here is continuous. We are dealing with weights, everything's continuous. Haven't got any continuity correction to worry about in this example either. So if we can do that, do the phi-ing. Again, you're going to get a phi of a negative, and you need to do the 1 minus phi of the positive thing for that. I'll pause it here, and we'll look at the answer in another clip. So the final working out for this one is on the board. And again, there's no continuity correction we've needed so far because we were starting with continuous data, weights of things. So at no point is discrete ever been involved in here. So everything was continuous all the way through. That's the answer for part B. So that brings us now then on to part C. And part C was when we had to look at the average weight of 25 chocolates and their average weight being between 9.9 and 10.1. And we've got this information at the top of the screen about W. So what random variable are we interested in part C? It's not the sum of them. What are we interested in now?
Individuals.
The mean weight. So we're interested in W bar. Okay, the average weight. This is where the central limit theorem comes in. How will W bar be distributed? Central limit theorem says mu and sigma squared over n. Yeah, that's right. So that will be how the mean of the sample is distributed. So here we've got it's going to be normal. Mu is going to be 10. And the variance is going to be sigma squared, which was 4, over the size of our sample,
25.
which is 25.
I thought last lesson you said that sigma squared over n was the whole thing squared.
That's
No.
sigma squared, just divided by n. That's
Okay.
right. Okay. So, what is, if you want to write that as a decimal, you can do. You can leave it like that in your calculators. And what we are looking for here is the probability that that is between 9.9 and 10.1. Again, can you make sure that when you're writing these down in questions, you're using this notation, we're writing these down as we're doing here. Again, we can do, if we like, a diagram. This is now W bar. I'm looking at the mean and the values. And again, I want the shaded bit. You can do it as we've done before. You can do it different ways if you want to. We'll meet up again in a minute and see if we all have the same answer. So the final working out for part C is there. You can see that. And we've got an answer, final answer at the end, 0.197. And it is someone said, it's very much like the answer part A, it is a coincidence. It's not going to be exactly the same. It is just a coincidence here in this case.
Is that
Okay, right. The next one. If a large number of samples of size n, don't know what n is, are taken, from a distribution that follows the Poisson distribution, 2.5, and about 5% of the sample means are less than 2.025, What do you think you've got to do?
Find the probability that you win a game.
No. You've got to find
N.
n. Okay. So this is like a backwards question, I suppose. Okay. Well, you've actually got a probability here, and you've got a value. You know you're dealing with sample mean, so that should be ringing Bell's central limit theorem. And you've got to find out what n is. And we're starting off with a Poisson distribution. So we'll say x follows the Poisson distribution. 2.5. That's a good starting point. That's using information we've got. But this question is talking about sample means. So the question is talking about x bar. How will x bar be distributed?
Is it 2.5 times 5%?
Well, hang on. We need two things here. We need. It will be normally distributed. Normally distributed. X bar always is. What's the first thing that goes in the bracket here? The mean. What's the mean of that Poisson distribution? 2.5. Okay. That was the mean of the Poisson. Then, for x bar, what comes after mu?
Standard deviation.
For x bar, yes, sigma squared over n. Sigma squared is the variance. What's the variance of that distribution? Variance of the Poisson is the same as the mean, it's lambda, yeah. So that's sigma squared over n, which I don't know. So the sample means are going to be distributed like that. Now, if I can link these two things here together, I am told that the probability that the sample mean is less than 2.025 is about 5%. That's writing that down in proper notation.
And then the amount.
Why?
Might be thinking, should I put 5.0.052? Because that's
Stick with this. No, okay, see, okay.
That's exactly 5%.
Yes.
That's not what I was
Okay, no. Keep with that number, and you might see where that comes from in a minute, but keep with that number for now. Okay. Right, now, it's a less than probability. That's fine. So we can go straight into phi stuff, phi notation. What will I start with inside my bracket?
2.025.
That number.
Minus 2.5.
Minus the mean. Yeah.
Whatever. Sigma.
Square root.
Thingy. Standard deviation.
Square root of
Which is
2.5 over n.
You're saying all the right things, but so what actually am I going to write down here? What is the value of?
2.5 over n.
2.5 over n is the variance. Yeah, I need to square root it. Square root of that goes there.
Square root the whole thing or just
Square root all of that.
all of it?
Yeah.
Okay.
So that's my variance of that distribution.
Yeah,
It's the standard deviation that comes down here. All of that bit gets square rooted. And I know that equals 0.05. Yeah, to find out what n is, because that's inside a phi bracket, the next thing I need to do is anti-phi both sides. Well, anti-phi on the left is just writing out again without the phi at the front.
1 minus the 5.
No, it's minus 5.
Minus 5.
And then over here I need to anti-phi 0.05.
I never can remember if you put the minus in front.
Right, yeah, that's something small. If we're anti-phying something small, we said we minus anti-phi something big. So we put a minus here and a 1 minus over there.
So,
Can I just write that down and then take your question?
Actually, don't.
Okay. So anti-phying 0.95, and the further we go into this S2 course, you will just know what anti-phi of 0.95 is. And it's one you can actually get from the table at the very bottom. 0.95 at the table at the very bottom, 1.645, and the minus sign in front of it. So now, if you put those two sides together and play around with that, you should be able to rearrange that and find out what n is.
29.98.
You can have that as an intermediary step if you want. What have you got? 29 point? Yeah. Okay. So, okay, I think we can say that our sample size then, what are we going to say our sample size was? Because we can't have 29.98 sample size.
You had to round it up to 30.
Yeah, we'll say that our sample size will be 30 then. So sample size was 30. Okay. So that's finished one main section of this chapter. What we still have to address, which we won't address today, will be, hang on, what if we don't know what the population mean is, and if we don't know what the population standard deviation and variance are, which we've just been told by the great god of statistics who just tells us. And you think, well, if he knows that, why can't I just text the answer to the questions? Pointless. But we'll deal with that issue next time. But right now, I've got a note here that we should be able to do exercise 4A. So, in our books, Billy just said it's the end of the lesson. Billy can't read the clock. 10 minutes. Go, Billy. Billy, that's on video. Naughty child. So, exercise 4A. Okay, exercise 4A, which in my book is on page 84. On page 84, okay? You should be able to do now those questions. We'll deal with what comes in the rest of that chapter next time. So we're now just going to spend some time up until the bell goes, doing some of those questions and at the same time reflecting on them. Yes. So far, every question we've looked at in sampling theory and to do with the central limit theorem, we've been told what the population mean and the population variance are. Bit of notation first of all. Population mean, what symbol have we used for the population mean? Mu. What symbol have we used for the population variance? Sigma squared. Yes. Okay. If we don't know mu, is there anything you think we could use in its place? Let's just go to a scenario where this may happen. Maybe, big tree out there, we are trying to work out the parameter about that tree. We've taken a sample of maybe 50 leaves from that tree. We clearly don't know what mu is. We haven't measured every tree. What could we use? Yeah, we use x bar to estimate it. That's right, okay. You use x bar, which is the sample mean, to estimate an unknown mu. And x bar here in this case is called an unbiased estimator. And I'll give you a definition of that in a minute. An unbiased estimator, because, and I think we did this before, the expected value of x bar is mu. In the long run, if you average x bar, you would get mu. And that's the definition of an unbiased estimator of something. If its expectation is the thing it's trying to estimate, it is an unbiased estimator. So x bar is an unbiased estimator for mu. Sometimes you'll see this symbol here, mu hat. With that little hat, that hat symbol is implying that it is an unbiased estimator. So, we know what mu hat is. What we need to know next is what sigma squared hat is. What will be our unbiased estimator for the population variance? It is this.
Is that a hat?
That's a hat.
No, I mean when it starts the watching.
That's an N. Okay? This is our unbiased estimator for the population variance. Does any of that at all look familiar?
If you're going to say sigma squared hat, is it that way around or is it sigma hat squared?
I honestly don't think it makes a difference. I would say sigma squared hat. Okay? That's just how I say it. I'm not saying that's right, but that's how I will say it, sigma squared hat. So, does any of that look familiar?
Yeah.
Why and which
series? Yeah.
Oh, is that
Variance.
Well, yeah, what's this over here?
Sample variance.
Yeah, that is a sample variance there. That is a sample variance. And the sample variance I'm going to denote as S squared for the sample variance. So the sample variance is equal to that. So that's saying that an unbiased estimator for the variance is n over n minus 1. It's like a little fiddle factor, S squared. Go on.
Is that the expectation squared, or is that
That's a big sigma there. Sum of, yeah.
So sum of
X squared.
or is it the sum of x squared?
It's the sum of x squared,
Okay.
not the sum of x squared. Okay? So, this down here is our unbiased estimator for the variance. I'm not at the moment going to derive that for you because it is extremely complicated and you haven't got to be able to do it. But if you want to see the derivation of that, it is in the books, in your textbooks. But what you need to be able to do is to use that. There is a reason for this n minus 1 thing. And if you've got calculators, on your calculators, you may already have come across a button on your calculator, sigma n, to work out the standard deviation from a list of numbers. You'll probably also find on your calculator sigma n minus 1. There's a little n minus 1 there as well. And this n minus 1 is this one here, it's that. It's this fiddle factor here in there as well. So I'm going to pause it now just to see if you can see on your calculators where you can find both of those things. Okay, last lesson we started looking at this. This bit here's a recap. What to do if you don't know the population mean and or the population standard deviation. This is the central limit theorem here in a nutshell, that the distribution of sample means, whatever distribution x comes from itself, is normal mu sigma squared over n. If we don't know mu, we use x bar instead, because x bar is an unbiased estimator for mu. The derivation for that can be found in the textbook, because the expected value of x bar is mu. We can write that down using this hat notation. A hat over something means it's an unbiased estimator for. So the hat over mu means an unbiased estimator for mu. Then we said, well, what happens if we don't know sigma squared? If we don't know sigma squared, our unbiased estimator for sigma squared, which is sigma squared with a hat over it, is our sample variance, but with this fiddle factor at the front. And again, you don't have to worry about the derivation of that, but you do have to know the result of that. There's a slight issue here in that some textbooks call this thing here, which I in words would call the sample variance S squared, and I call that S squared. However, your OCR textbook calls it with the fiddle factor S squared. And this is confusion between different authors, effectively. Rob?
Why do you have the little n minus 1 thing to do?
Where's it come from?
Yeah.
It comes from a derivation which you saw a few minutes ago. Okay? Is the answer, which is also in the book. So, sigma, I will use notation like this. The unbiased estimator for sigma squared is that fiddle factor times by S squared, where S squared is the variance of the sample. So that's the notation that I will be using. So I'll just pause that there in case everybody wants to make any notes and then we'll carry on.
2 seconds.
What we're going to do now is just do a numerical example of this, okay? We are dealing now with a population with an unknown mean, which we will call mu. And this population also has an unknown variance, which we will call sigma squared. Now we have taken a sample of size 10 from this population, and I'm going to read out now the values we have got from our sample. So our values are 12, 8, 11, 10, 8, and 8, 13, 9, 11, 10. So those are our sample values. If you wanted to, you could call the first one, that's x1, that's x2, that's x3, then here that would be x10. So what we're going to do now is we are going to find unbiased estimators for mu and sigma squared. And if I use my other notation, I could say we are going to find mu hat and sigma squared hat, because that's what that means. So, from what we saw on the previous page, how do I find an unbiased estimator for the mean mu? What do I use as my unbiased estimator for the population mean that we don't know? Well, you just actually use x bar, because the expectation of x bar equals mu.
Yeah.
We use x bar. So x bar is simply add up all your x values and divide by how many there are. If you want to do that, you can do, or I can just tell you the answer. If you add those up, you get 100.
Is that divided? Yeah.
So divided by 10, 10. Because the mean of our sample was 10, our unbiased estimator for the mean of the entire population is also 10. The other thing we need to work out then is our unbiased estimator for the variance, which is sigma squared with a hat over it. And this is the thing where we have that fiddle factor. We have the n over n minus 1 times by s squared.
Is this in the book, like in our green book?
This may not be in the green book, no, I'd have to check. And that s squared is the sample variance. And the formula for the sample variance, the easiest one to use, is that formula down there. I'm just going to pause there for a minute. So all we're going to do now is just use our calculators and use this data to work these things out. Well, n here is 10. That was our sample size, so that's 10. That's 9. Sigma x squared is square each of these values up here and add them up. You could do it on your calculator. If you don't believe me, you can check it yourself at home, but it's 1028. N, our sample size, is 10. We actually worked out that x bar is 10. So that calculation will tell us what our estimate of the population variance is. Now, can somebody tell me, because I actually haven't got it here, what this value inside the bracket is? 2.8. It's 10.28 take away. Yes, okay. Say that again, sorry? 2.8, yes. Okay. So, whilst 2.8 is our sample variance, our population variance will be 10/9 of that. If somebody can tell me that.
3.1.
Yeah, I've got 3.11. Okay. So we had our sample. Our sample variance was 2.8. We apply this fiddle factor, and this down here, this 3.11, is our unbiased estimator for the unknown population variance. And what I'm going to look at in a minute with you, again, is just seeing if we can get those two things out of a calculator. I'm not going to video this next bit, but a challenge for you is, depending on what model of calculator you have, put these numbers up here in the statistical memory, find a button which will give you 2.8, which will probably be a sigma xn button, and find another button which will give you 3.11, which is probably sigma xn minus 1, or some sort of notation like that. But calculators should give you both of those values. There's one other bit of terminology which you might come across in some questions, and that's the phrase, the standard error of the mean. The standard error of the mean is basically sigma squared over n square rooted, which is sort of what it's got here. Sigma squared over n square rooted. If you square root top and bottom, you get that. And if you're talking in terms of unbiased estimators with hats on, those two are just those two. But if they're talking anywhere about the standard error of the mean, they're talking about that one there. That's the sort of most basic one. And that is the same thing as when you're using the central limit theorem and you say x bar is normal mu sigma squared over n, it's the square root of that. So in other words, the standard error of the mean is the same thing as the standard deviation of x bar. You will come across a question that I give you at some point which uses this phrase. So you just need to be aware of what that phrase is. The standard error of the mean is the same thing as the standard deviation of x bar, and if you're which is that or that, and if you're using unbiased estimator versions, they just have hats on. They are all meaning the same thing, and you just need to be aware of that phrase.